And we're going to continue today to, I forget, this is never going to be long, to explore Laplace transforms. In particular, today I want to talk about what I'll call the shift equation. And we're going to apply them to differential equations. So we'll see how we can actually use the Laplace transform to solve something. So last week, you'll recall, we said, okay, if you have some function f of t, you can define the Laplace transform. That this is a function of a different variable s, right? And the definition here was the improper integral from 0 to infinity of f of t times e to the minus st dt. And we derived this. We showed how this was a very natural generalization of the process that we call the discrete transform, which took a sequence and turned it into a power series. If we took that sequence and turned it into a continuous function and applied the exact same methodology, that we ended up with a continuous transform. And after some algebraic gymnastics, we ended up with this wonderful equation. Okay, and then we worked some examples. For instance, we said if you start with the function 0, then the Laplace transform is 0. If you have the function 1, you got 1 over s, for s greater than 0. And we remember what s became?
2 over s squared.
2 over s squared, is that right?
Hmm? 1 over s.
1 over s squared. Why? Well, what was the general formula? If you had s to the n, we're here, n is a natural number. What do you get? N factorial over s to the n plus 1.
I was just testing.
No, well, you were right up to a constant. Not so bad. Okay. So we said at the end of Thursday that what this seems to do is take a function and make it slightly more complicated. Yeah? Okay, 0 didn't get any worse, but 1 became 1 over s. It's not bad, but it's a little more complicated. And each one of these gets more complicated in some reasonably nice way. But I want to start today by showing you an example where the function, I think, really becomes nicer. So let's try to compute the Laplace transform of an exponential. So here a is just going to be some parameter, right? Some constant. Okay, well this is reasonably straightforward. All we have to do is plug it into the definition. So let's see, this is the integral from 0 to infinity of e to the at times e to the minus st dt. Okay, fine, no problem. We combine this. E to the, let's see, that's a minus st dt. Okay, now I just play a little trick. I make this e to the minus s minus at. All I did is introduce a minus sign and then reverse the order to compensate. Okay, now why, of course, am I doing this? Well, let's look back to the definition of the Laplace transform, right? It's some function, whatever that is, times e to the minus some variable times t. So all I'm doing over here is changing the variable from s to s minus a. And then what's the function out front? Well, the function, you think of it as just a 1. It's just a 1 over here. So this is really just the Laplace transform of 1 with respect not to the variable s, but the variable s minus a. And so the answer is just, well, 1 was 1 over s, but if we do it going to s minus a, it becomes 1 over s minus a. And instead of s being greater than 0, what does s have to be? S has to be greater than a. Right? You're doing that so that this is positive, so that this will converge. If this is negative, then what's going to happen? Well, then it'll get e to a positive power. And of course, that's not going to converge when you go from 0 to infinity. Okay, so we get something new to add to our list. E to the at becomes 1 over s minus a, where s is greater than a. So we actually, in this case, have really simplified something, right? We've taken an exponential and just turned it into, I mean, look at the difference between the Laplace transform of 1 and e to the at. It's just got a little minus a down there. That's really quite nice. Okay, so we messed something up?
Yeah, all of your f of t's are s's.
All of my,
Column
oh,
F.
yeah, of course this should be t, and that should be t. That's right. Very good. Okay, so if you think back to, Algebra 2, pre-calculus, calculus, and so forth, you'll remember that there are more functions than what I've written down on the board, amazingly. So it's interesting to know the Laplace transform of all of them, but of course we don't have that kind of time. So we want to give some shortcuts. But before we go into those, I want to give you an example of how we can use the Laplace transform to solve a differential equation. So since we don't have so much theory yet, we need just a little bit of theory to say that we can actually compute the Laplace transform of a derivative. So I think I've started trying to number these things because Karen and Zuen told me I should number things more often. Okay, so this is going to be 4.1 theorem. So now you can refer to theorem 4.1. So if f of t is a continuous function such that two things hold. Just two? Yeah, good. So first, the derivative of f is, well, in this theorem I'm going to write down something in parentheses and then something not in parentheses. And the thing in parentheses is true. The thing that's not in parentheses is what I'm going to prove. So if the derivative of f is piecewise continuous. Okay, so remember what piecewise continuous means. Your function looks like continuous, 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 right? You have some problems at a few endpoints, right? Where you might get jump discontinuities like that, okay? But aside from these places, it's a continuous function, okay? Now, to prove this for piecewise continuous just requires a little bit of bookkeeping. There's nothing really interesting going on. And the reason why is, of course, when you integrate, right, over a region, if there are discontinuities at just a finite number of points, it doesn't matter. Right? The integral doesn't care about just a few points. It cares about the continuum of points, right? Okay, but I don't want to do these little manipulations, so I'm just going to prove it in the case where you have a continuous function. But it's true for piecewise. So if f prime of t is continuous on any interval 0 to a, and if, so the second thing is going to be, I'm going to call it the growth condition, or maybe I call it the growth hypothesis later. Let's see, hypothesis. We're going to call this the growth hypothesis. Is that f of t doesn't grow, well, it grows slower than an exponential function. F of t grows slower than an exponential function. Okay, so what do I mean by that? So what I mean is that if you look at the size of the function in the long term, it's less than or equal to some exponential function. So f of t is less than or equal to k times e to the at, right, for all t greater than or equal to some m. Okay, so m is some point where it starts being less than or equal to it. Really small t, it might be bigger than an exponential, but you don't care. You just care in the long run, f of t gets dominated by an exponential. And of course, the reason why we want that is when we start computing these things, we know what happens. You end up getting, oh yeah, this thing's going to 0, this thing's going to infinity. And you want to know what's the limit going to be. So you have infinity times 0, where's it going? Right? And so you want this growth hypothesis to ensure that, the f of t is going to infinity slower than the exponential function is going to 0. And so the whole limit is going to be 0. Okay? And so here, k, a, and m are positive constants. Okay, so that's all the hypothesis. We don't even have room on the bottom for the conclusion. All right, so let's get the conclusion over here. Then, so if you have these two conditions, the derivative is continuous and you have the growth hypothesis on f, then the Laplace transform of f prime of t exists. So if you know that you have these conditions on f prime and on f, then you can take the Laplace transform of the derivative of f. Right? And then at least it exists for s greater than a, where this a is the same a that you had over here. It's the a that you're using to bound the growth of f. Okay, but it's not so wonderful for practical purposes knowing that this Laplace transform exists. What is really practically useful is knowing what it is. So the Laplace transform of the derivative equals s times the Laplace transform of f minus f evaluated at 0. Again, this holds for s greater than a. Okay, so we need to prove this because we haven't proved so many things. All right, so let's see. If we want to compute the Laplace transform of the derivative, well, we plug things into the definition and see where we go. So the Laplace transform of the derivative equals the integral from 0 to infinity f prime of t e to the minus st dt. Okay, so what are we going to do with this thing? Well, what integration method would we like to use? It's the only one that we typically want to use with Laplace transforms.
By parts.
By parts, right? Okay, you got a product of functions by parts. And, well, typically we want to use this exponential as the thing that we integrate. But this is one of the few cases where it actually makes some sense to integrate this one, because you know what its integral is going to be. It's just going to be f. Right? Okay. So here's what we're going to do. We're going to use our table method. Okay. So we'll put e to the minus st on the left and f prime of t on the right. Okay. So the derivative is minus s e to the minus st. And the integral is f of t. Okay? And from here we're actually going to stop, because really what more can we do? We can't integrate this anymore and get anything we like. So we just stop here. And whenever you stop using this tabular method, you just go across. Right? If you don't have a 0 here, then you just go across. And you do plus, minus. And if you think about it, this is exactly what integration by parts tells you to do. Right? This is... so the integral of u dv, right, is u times v times the minus the integral of v du, and that's all it is. Okay, so what does that tell us that we're going to get? So here, right, we get f of t e to the minus st, but we can't forget about these limits. Okay, we have to take that limit there. So it's going to be the limit as b goes to infinity of f of t e to the minus st minus is plus the integral from 0 to infinity. What do we want? There's an s, which is respect to t, so we can pull it out. F of t e to the minus st dt. Okay, so I'll pause there, because that's a lot to process. Questions? Are you happy? Zuin's not happy. Kaiwei's not happy.
I said Zuin's not happy.
Yeah, oh, okay, Zuin's not happy. Okay, what are you not happy about?
Why do you have integrals on the second pattern?
Well, let's remember your integration by parts formula. Integral of u dv equals uv minus the integral of v du. Okay? All I've done here is remove the u's and the v's, of course, to write this down. So there's u dv. Okay? So it becomes uv minus the integral of v du. Right? There's the integral of v du, and I pulled the s out. Okay, I'm just applying this formula without calling things u and dv.
Are you forgetting the bounds, the first part? When that's before the infinity of what?
Say it again?
Are you forgetting the...
Oh, yeah, we need to, of course, yeah, that's true. We need to put 0 and b here. Yeah, you need to evaluate this at the endpoints. 0 and infinity, or in this case 0 and b, and let's take the limit. Yeah, thank you. Okay, so this part is quite easy. That's the Laplace transform of f. And then you multiply it by s. Okay, so you have s lf of t. Well, of course, that's exactly this right here. So what you're hoping, what you're expecting is that this limit just evaluates to negative f of 0. Okay, well, let's see what happens. When we plug in b, right? Okay, this t becomes a b. As b goes to infinity, what happens to e to the minus sb? That goes to 0. Okay, but now f, what's happening as b goes to infinity? Well, we don't know what it's doing exactly, other than it's bounded by an exponential. And I claim that that means that that product is going to go to 0. Because one side is going to 0 and this is bounded by this exponential. Okay, but we can prove that. Let's do a little side work here. Let's look at f of t e to the minus st. Let's look at the size of that thing. We know that this is equal to, well, you can break this up. And when you break it up, you get the absolute value of both. And since the second term is always positive, you can drop the absolute values. And we know that f of t is bounded by k e to the at. So this is less than or equal to k e to the at times e to the minus st, which is k e to the a minus s times t. Right? At least, right, for all t greater than or equal to m. Once you get past a certain point. And since we're going to let t go to infinity, that's okay. So, for s greater than a, this is negative. Right? Which means as t goes to infinity, this is going to 0. So this goes to 0 as t goes to 0. So then if the absolute value goes to 0, then of course the function itself must be going to 0. Okay, so that helps you with the b part of it. Now what about the 0 part? Well, you get f of 0 times e to the 0, which is 1. So you just get f of 0. And so, of course, you're subtracting when it's 0, so you just get s lf of t minus f of 0. Okay, so the fact that the b part is going to 0, that's kind of okay, so that finishes the proof. I think we're ready for the example. Yeah. Before we do it, I'll pause again in case anybody's unhappy. I don't care about your personal life, but at least for this proof.
I was going to say.
Yeah, I know, it's none of my business. Unless I'm the one causing the problem in your personal life. Okay. So last week we wrote down the following differential equation. And I think we did it in the context of interest rate on a bank account. So A of t is the amount of money you have at time t. You start with p dollars, and you know that the rate that you, or the, excuse me, the interest that you get, right, depends on the amount that you have in there. Right? So the rate of change is exactly equal to the interest rate times the amount you have in the bank account. And we saw this is just a nice separable differential equation. You can move the dt to the other side, divide by the a, t, right? Integrate both sides and solve it. Okay. But let me show you a way to do it with Laplace transforms. Straightforward. So first, let me rewrite this slightly. I'll just write this as a prime equals Ra. A little shorter. And now I'm going to take the Laplace transform of both sides of this differential equation. So I get L of A prime should equal, oops, should remember the L of Ra. Okay, now R is a constant. What do you think we can do with constants?
Pull them out.
Yeah, pull them out, right? Okay, so in some instances the pull-out method doesn't work, okay, but in this instance, you're right, it will work. Okay, and you're actually going to prove that on the homework. What, man? No. Okay. Okay, so this is half of what we usually call linearity, and on the homework you'll prove it, but I'll write it down after this problem. Okay, so L of A prime equals R times L of A. Now, we just wrote down a formula for the Laplace transform of a derivative. So let's use that. So L of A prime is S times L of A minus A of 0. This is very good. The Laplace transform method has a wonderful little positive externality. It automatically is going to incorporate the initial value that we give it. Instead of coming up with some constant that we then have to solve for at the end, it's going to put everything together all at once. Okay, so that's the L of A prime. And on the other side, we still get R L of A. Okay, so now we do the only thing that comes natural. We solve for L of A, and we plug in our value for A of 0. So let's see, I can subtract, and I'll get S minus R times L of A. And then what? I have to move the A of 0, which is P, to the other side. So this equals P. And then I'll divide by S minus R. So L of A equals P, which is just a constant, over S minus R. And this should work for S greater than R. Okay, so whatever the function A is, we know its Laplace transform is P times S minus R. Times, divided by S minus R. Okay, well let's go back over to our little table. And you'll note that, well, if we had an S minus A, we'd be okay. We have an S minus R. Okay, it's just a letter. We don't care. We should get e to the RT. Okay, but there's this extra P. But that's just a constant, right? The linearity property, right? The fact that you can pull constants in and out is just going to say, oh, just put a P out front. So this tells you that A is actually P times e to the RT, which is exactly the solution that we got by separating. The difference, the reason why this is a little more versatile, is you don't need to have a separable differential equation to use this method. Now, there is a very good objection that you should be raising at this point, because I'm cheating, almost. I mean, I'm not cheating because there is a theorem that allows me to do this, but you should say, you haven't shown me that theorem, you're cheating. So, what did I do? I started with a differential equation. I took the Laplace transform of it. I did algebraic manipulations, and remember, that was the whole goal, right? We wanted to turn a differential equation into just solving using methods from algebra. And then we got down to the end where we said, my Laplace transform equals this, and therefore I can conclude the original function looked like that.
We proved we could go backwards.
We didn't prove you could go backwards. What do you mean we didn't prove we could go backwards?
Well, we only have a long way.
So certainly, okay, if I have that function, right, I know its Laplace transform is over there.
But you do not know that
you're not sure.
But you don't know how you can apply this theorem.
I don't know how what?
Or you don't know why you can apply this theorem. You didn't.
Oh, you mean that what? I didn't verify all these things. Okay, well, of course, I have to assume the hypotheses. You're right, right? I have to say, okay, assume that this A satisfies, well, for instance, it should be a continuous function, right? And, all right, I'm sorry, the derivative, right? The derivative should be continuous, and I need to know that the I need to know the derivative is continuous. I need to know that this function A should grow slower than an exponential function. Okay. So let's assume, though, that I've done that. Even then, there is a small problem, and Charles and Christina are getting closer to saying it. I know how to go this way. And it is certainly true that if I have this function, and I know that it is the Laplace transform of some function, that this is a possibility. Exactly, right? I haven't proved it's the unique possibility. Right? How do you know there isn't some other function whose Laplace transform is 1 over s minus a? Okay, that could be. Okay, so it turns out that's not a problem. The Laplace transform really does, more or less give you uniqueness. So if you know the Laplace transform, you can take what's called the inverse Laplace transform. Okay, so we're going to have a whole section on that where we fiddle with those things, and we'll even see some complex analysis in the midst of it.
So it's bijective?
It's essentially bijective, yeah. Okay, so but that is something that you should at least worry about. Anytime somebody does this sort of process and they go one way and then they say, oh yeah, you can just go backwards. Of course, we know that there are some functions that aren't one-to-one. Okay, so let me. I hate to take off the chart. Maybe I'll quickly move the chart over. But we don't need everything in there because there's some redundancies. So if you have f, L of f, we know that t to the n becomes, what does t to the n become? It became n factorial over s to the n plus 1. And we know that e to the at becomes 1 over s minus a. Okay. Oh, and we also know that f prime becomes s LF minus f of 0. Okay, so you're going to start building this table that you can refer to. Now, one problem that you might notice is that we've only given you the Laplace transform of one derivative. And some differential equations could have, say, a second derivative. Okay, so we'll have to remedy that. But that's not so hard to deal with. But first, let me give you the theorem which you'll prove on the homework. It's not hard. Is that me? That could be. All right, so the theorem is that the Laplace transform is a linear operator. I.e., if f and g are, I don't think I need anything interesting here. If f and g are functions whose Laplace transforms exist for s greater than a and s greater than b, respectively. Okay, so that means that the Laplace transform for f exists for s greater than a, the Laplace transform for g exists for s greater than b. Then, oh, and let me see, and c, let c be some real number. Then two things hold. First, the Laplace transform of f plus g, right, the sum of the functions, is the Laplace transform of f plus the Laplace transform of g. So it's additive. And for what s? Well, here for s greater than the maximum of a and b. So the f1 only works for a, the g1 only works for b, and the sum is only going to work for whichever a or b was bigger. You have to at least start as big as the biggest one. And the other one is what we already used. It says if you multiply a function by a constant, the Laplace transform is changed only by that constant. Okay, so that's, of course, very easy to prove if you think about the definition of the Laplace transform, right? It's just given by an integral, and of course we know integrals are linear. So that shouldn't be hard, but of course this is very useful. Now, I'm going to write down one more technical thing, which is that essentially these same, we'll forget about the f prime of t, but this growth hypothesis, this is going to ensure that the Laplace transform of a function exists. So that's just something nice to have around, so that we know we can take Laplace transforms of reasonable functions. Yeah. Theorem. And hopefully we won't have too many more nasty theorems around. So, if f is a continuous function, on 0 to a for all a greater than or equal to 0, and f satisfies the growth hypothesis, which if you forget what that is, it's just thinking over here. Then the Laplace transform of f exists for s greater than a, where again a comes from the growth hypothesis. A. It's this parameter in the exponential that bounds the function. Okay. And the proof is exactly the same, really, as for theorem 4.1. So I won't retell it. Let's see. I don't know if I want to prove this next one. Maybe I won't. Maybe I'll just state it. Okay. So I want to solve this problem of what if you have higher derivatives? Let's see. Oh, we'll add to our table here. F plus G goes to LF plus LG. CF goes to CL of F. Okay, so this will have some hypotheses, and you'll see as we read off the hypotheses, they're basically just meant to mimic what we did in 4.1. So let f be continuous such that, okay, so in 4.1, we wanted the derivative to be piecewise continuous. In this case, I'm looking not just at the derivative, I'm actually trying to take the Laplace transform of, say, the nth derivative. So I'm going to need more to happen. In this case, I'm going to want the first n minus 1 derivative to be continuous. So remember, this parenthesis notation means taking the n minus first derivative, right? So these are continuous. The second thing is that the nth derivative is piecewise continuous, right? Although we're only going to treat the case where it's honest to goodness continuous. Well, I mean, we only proved it for 1 in that case. If the first, well, the original function and then all the derivatives up to the n minus first derivative satisfy the growth hypothesis, so they're all bounded, all right, by an exponential, but in fact, I want them satisfying it for the same k, a, and m. k, a, and m, then the Laplace transform of the nth derivative of f exists for s greater than a, and we can write down a formula for it. And that's, of course, what we're really interested in. So it's going to equal, well, before it was an s times the Laplace transform of the function, now it's going to be s to the n times the Laplace transform of the function. And then you have to start subtracting off terms. So last time you just have to subtract off an f of 0, but now we have to go down a lot. So we start by decreasing the exponent on the s and multiplying by f of 0. And then we continue to decrease the exponent on the s, and we add derivatives of f evaluated at 0. And we just keep going until we run out of s's. Right? So you get an s, what do we, I guess it's f to the n minus 2. Right? They should always add up to n minus 1. And then the last one is f n minus first derivative at 0. Okay, so the nice thing, though, is that only one term gets a Laplace transform. Right? That's the first term. Everything else is going to incorporate initial value data. Yeah, I know it gets over there pretty far. Okay, so let's say this again. The Laplace transform of the nth derivative of f is s to the n times the Laplace transform of f minus s to the n minus 1 times f of 0 minus s to the n minus 2 times the derivative of f at 0 minus dot 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 minus s times the n minus second derivative of f at 0 minus the n minus first derivative of f at 0. We can shorten this up a little bit if we use summation notation. So L nth derivative equals s to the n Lf minus the sum. Okay. So what's going to happen here? You're going to have an s to the I, and then you're going to have an f to the, well, I plus whatever goes up here needs to add up to n minus 1. So this is going to be n minus 1 minus I, or n minus I minus 1 derivative at 0. So here I, well, you can run it either way. Since I put the s to the n over there, it'll be the last term, but it'll go from 0 to n. No, n minus 1. So then you get n minus 1, and then n minus, yeah, good. I think that's right. Okay, so maybe an example will be illuminating. No? Okay. So. Let's try the differential equation y double prime minus 3y prime plus 2y equals 4e to the 2t. And I'll give you the initial information that y at 0 is minus 3, and y prime at 0 is 5. Okay, so this is already far more complicated than the separable differential equations that we saw. And you have no idea how to do it if you have no Laplace transform. So, well, we have the Laplace transform, so we might as well try it. So we take the Laplace transform of both sides, and we get the Laplace transform of y double prime. Right? And then, of course, here's the nice thing. We're using linearity already, right? It's a sum here, but we can break it up, and we can pull out all the coefficients. 3 times the Laplace transform of y prime, 2 times the Laplace transform of y, equals the Laplace transform, well, let's see, we'll pull the 4 out, of e to the 2t. Okay, so first we'll do the L of y double prime. So this formula says if you're taking the second derivative, then you can rewrite it as s squared times L of f, or in this case L of y. So s squared L of y. And then you have to start subtracting off, right, s times these initial values. So we'll decrease the exponent of s by 1, so that'll be an s, and then we need y of 0. And then we decrease the exponent of s again and get y prime of 0. Okay, so this bit corresponded to that. Okay, and then we need minus 3 L of y prime. Okay, that we just did. There you have to do s L of y minus y of 0. And then finally 2 L of y. Okay, and what does that equal? Well, it equals 4 times the Laplace transform of e to the 2t, and that we know. E to the 2t becomes 1 over s minus 2. And then we have it multiplied by 4, so we get 4 over s minus 2. Okay, and in the back of our heads, we know this is working when s is greater than 2. Okay, so we've turned this differential equation now again into an algebra problem. Right? We just have to solve for L of y. So let's see here. I have an s squared and a minus 3s and a 2 times L of y. Then I have, okay, y of 0 is minus 3. So this becomes a 3s. And then over here, see, I get a minus positive 3 times y of 0, so minus 9. Oh, there's no s there. I wanted one with an s, but there's no more s's. So yeah, so we'll get here. Minus y prime of 0 is minus 5. And then, what did we say? This is going to be minus 9. Yeah, 3 times minus 3 is minus 9. Did I get that right?
I think it's plus.
Where's the plus coming from?
No, it's a minus.
There's a minus, and there's a minus.
Then another minus.
And then there's one more minus. So we got 3 minuses.
Oh.
Okay, so minus, minus, minus is minus, and then 3 times 3 is 9. Good. And then this equals 4 over s minus 2. All right, and of course this is just minus 14. Okay, so this is no longer calculus or anything like that anymore. I mean, this is really just how do you solve these things. Okay, well the first thing I would do is factor that. You know, that's such an easy one to factor. Let's see. Good. Everything's consistent. Every once in a while in 265 this would happen where I work through a problem on my notes and get it wrong, but I'd be doing it right in class. And then I would get really confused because I do it right in class and we couldn't find a mistake. I'm like, yeah, but my notes say I'm wrong. But it was usually my notes. Okay, so what are we going to do here? Well, this we know, I said we can factor. That's, what is that? That's minus 2 and that's minus 1. Okay, good. So let's see here. I'm going to move this over to the other side, and I want to put it over an s minus 2, right? So that everything's on a common denominator. So let's see here. I'll leave it like this for a little bit. S minus 2, S minus 1, L of F, L of Y equals 4. Okay, so I subtract it and multiply it by S minus 2. So minus S minus 2 times 3S minus 14. Okay, over S minus 2. Okay, and then of course I can divide, and I get L of Y equals, okay, well the bottom's easy. That'll be S minus 2 squared times S minus 1. The top, all right, let's see here. I have a minus 3S squared, and let's see, plus 14S and plus 6S is plus 20S. Or is that one too many? Yeah, minus plus, okay, plus 20S, and then minus 28. Tell me, please double check my arithmetic. No, I got 24 on my.
You got 24. How do you forgot?
It's plus 4.
Did I? Oh, I forgot the plus 4.
Yeah.
There we go. Good, good, good. Yeah, can't forget that plus 4. Okay, so is this function in our list? Does not appear so at the moment. Okay.
Wait, I know.
Yeah.
Partial fraction.
Partial fractions, of course. All right, you can break this up. Now, it's actually, in the end, we're not going to have everything when we do partial fractions in our list, because what is this going to look like when we break it up? You're going to have an s minus 1. Okay, that's fine, right? We know that's going to come from one of these. You're going to have an s minus 2. Again, that's fine, it's going to come from one of these. But you're also going to have an s minus 2 squared. That's not in that list yet. So we'll have to resolve that. Okay, but in any case, let's remember how to do partial fractions. So minus 3s squared plus 20s minus 24 over s minus 2 squared times s minus 1. We want to break this up as a over s minus 1, say, plus b over s minus 2 plus c over s minus 2 squared. Is that right? Highway, you seem so thrilled. What's that?
Cover method.
The
Cover when you cover the denominator.
Yeah, we're going to use the cover method here. If you want to know what this A is, it's really quite nice, because all you have to do is see what happens when S is 2. Right? Because when S is, well, let me write it in a different way and you'll see what I mean. But then we'll go back and show you. So if you multiply both sides by this denominator, we'll get a times s minus 2 squared plus b times s minus 1, s minus 2. Actually, I said s is 2, I mean s is 1. Oops. Okay. So I cleared the denominator. So if I set s equal to 1, then these terms die. Right? And you're just left with the a times, well, when s is 1, you just get 1 here. You just get a. So a is exactly what you get when you put s equal to 1. So the way that you can see that from the original thing is you just say, okay, you want this a, right? You forget about the other things, right? And you just plug 1 into here. And it's really, that's what it's saying. Do that. Okay, but in any case, when a is 1, and when s is 1, we see a equals what? Okay, minus 3 plus 20, 17, minus 24, minus 7. Did I do that wrong? Minus 3 plus 20, 17 minus 24 minus 7. Okay, now if I want to get c, I let s equal 2, because that'll kill these guys. So when s is equal to 2, everything dies except for the c when you get 2 minus 1, which is 1. Okay, and then over here with a 2, okay, you get 4 times minus 3 is minus 12. Minus 12 plus 40 is 28. Minus 24 is 4. Okay, now how do you get b? What's that? We can plug in a and c, right? We know what a and c are now. We can plug those in and then expand everything out. Okay, that's the algorithmic way to do it. This is a long process, though. You have to do a lot of expanding. There's no way that you think, oh, obviously this is the way to do it. But there's kind of an easy thing to try, which is s equals 0. Right? Well, why s equals 0? Well, s equals 0 at least makes this left side really easy to compute. You get minus 24 on the left. And on the right, well, you know what a is. It's minus 7. And when s is 0, this becomes 4. So 4 times minus 7 is minus 28. Plus, okay, well, let's see, b times 0 minus 1 and 0 minus 2. It's just 2, so 2b. And when s is 0, you get minus c. And c was 4, so minus 4. Okay, so this is much easier than expanding everything out. So let's see here. That's minus 32, add it over, you get 8, right? So 2b equals 8, so b equals 4. Okay, so up to arithmetic errors. So let's see. My calculations agree. Good. So we now know that the Laplace transform of y equals, okay, minus 7 over s minus 1, and 4 over s minus 2, and 4 over s minus 2 squared. And so, inverting the process, we get minus 7 e to the minus, we use minus or positive t. Okay, so s minus 1 corresponds to when a is 1. Let's get e to the t. And then 4e to the 2t. And then we don't know how to do this last one. But I'll tell you what the answer is, and then I'll give you a hand-wavy explanation, and then we'll prove it later. It's going to be 4t e to the 2t. Almost the same thing. But this square somehow introduces another t. And I'll at least give you, let me give you a couple examples to make you believe that this could be true. Okay, so if you take 1, the Laplace transform is 1 over s. If you take e to the at, you get 1 over s minus a. Yeah? Okay, that's the first one I wanted to give you. Where's my second one? Yeah. Then I just said, well, we know if you have t, you get 1 over s squared. And I just said that if you have t, e, I wrote to the 2t, but of course I could mean to the at, then it became 1 over s minus a squared. This suggests, well, f of t goes to, we call it, sometimes called big F of s. What then should f of t e to the at go to? see, 1, which you could put here if you liked.
F of S minus A.
Yeah. Look at that. E to the AT shifts it by A. E to the AT shifts it by A. So a reasonable guess is that E to the AT is going to shift any function by A. This is why it's sometimes called shift property. Okay. Okay, so maybe we should try to prove that.
Maybe.
What's that?
So maybe we should.
Yeah, but the proof is we've already actually seen the proof. It's very easy. If you want to compute the Laplace transform of f of t times e to the at, then this is equal to the integral from 0 to infinity, f of t, e to the at, e to the minus st dt. That's just the definition. You combine these terms, e to the a minus s times t. You play this trick, f of t e to the minus s minus at. And then you say, but wait a second, this is exactly what you'd get if you did the Laplace transform, but replaced the variable s with the variable s minus a. So this is f of s minus a. It was kind of strange. E to the at, this weird exponential function, all it does is shift things over by a. So we can add that to our list. We have f of t e to the at, it becomes f of s minus a. That's quite nice. Oh, I guess we should write this implies y equals. So yeah, by the way, we solved the differential equation. A non-trivial differential equation, right? This is not one that we had a method for before. This is not one that you probably would have guessed the answer. Right? Remember this one we did first with the bank account, right? That one we said we couldn't even guess that. We didn't need to use separable theory or anything, right? We could have guessed it. This one, I'm not guessing that. So we've really solved a problem that we couldn't solve before, which is nice. And we didn't have to solve for constants at the end, because again, the Laplace transform process automatically, when you use this theorem, it uses the initial value data. So it fits it right in for you. So it's really cool. Okay.
So,
yeah.
will you y0 to -3 and with drive 0 to 5? Will you use that?
Where did we use it?
Yep.
We used it here. When we evaluated the Laplace transform of the first derivative and the second derivative, we had to use y of 0 and y prime of 0 and then y of 0. We actually use those. Okay, so I won't go any further, except I'm going to write down 2 formulae that are useful for us, and we'll talk about them more tomorrow. And you guys, I won't prove these formulas. You can prove them on your homework. But well, you might guess a couple of functions that we'd like to know the Laplace transforms of, especially given some of the differential equations we started with at the beginning of the course. So for instance, it would be really nice to know the Laplace transform of sine and the Laplace transform of cosine. And they're very, very similar, as you might expect. So they're both going to be over s squared plus a squared. And well, one of them has an a on top, and one of them has an s on top. And the best of all possible worlds is if the s would be up here next to the sine, right? Sine with s, but it's not the best of all possible worlds. It's exactly the opposite of what you want. So the s goes down with the cosine, and the a goes up with the sine. Okay. Oh, and I should mention this works for all s greater than 0. Okay. So tomorrow we'll pick up there and work a couple examples with those. The new homework is up online. As Ben pointed out, and I posted on the web, the first homework there was a slight typo on exercise 2C. The first equal sign should be a minus sign. When you try to solve it, you'll of course see that you can't.
Because if we apply the Laplace to the equation 2 for the first homework.
Oh yeah, here, let me write. I'll just write that down. So, oh, you have the new version, don't you?
Oh yeah.
Yeah, okay. So it used to say y prime equals 2ty equals 1. And this equal sign was the problem. It should say y prime minus 2ty equals 1. I'm going to remap my keyboard so that the minus sign is not next to the equal sign. All right, this was problem 2C on the first homework. Okay, very good.
Now this one,
Go ahead.
I didn't know that.
It's more not related to class.
I know, I actually have my own website. So here, bring over those notebooks right on top. Okay, here's the short. Well, the short way is just Google my name. But I don't post my notes for no particularly good reason other than I'm lazy. But